Yorong, and identifiability of nonlinear ICA.
Yeah, hi everyone, I'm Yorong, and I can talk about this paper on the identifiability of nonlinear ICA, sparsity and beyond. And I was hoping before I can cover the light lightning part function classes that paper, but which I couldn't. If Rogers and Xinhui can talk something of them, I'll be glad. And please stop me at any time because for now I haven't fully understand this paper. I just try to deliver information step by step, and we can talk and discuss at any time. And I think everyone, 99% in our lab should know the blind source separation things. And but I'll go through from zero, like in the area we have different sources from different peoples, and we have microphones or sensors to collect the sources, and like image right left here, and we'll have we'll give a weight of each of these sources when the sensors from different location directions to collect the sources, and we consider it as the linear combination and give the weight. The matrix A is the linear combination of them, and we have like the observed data X. The only thing we have is kind of unsupervised learning and do some methods and to get back, and finally we can get the original sources. This is basically what independent component analysis is doing. And at the beginning of I learning about ICA, I was asking question for what's the difference of PCA and ICA, and kind of from this plot we have the two uniform sources combined, and by mixing them, we have got it to be rotated, stringent. And for what PCA does it to kind of like a wedding precise and get the shape of it, but the rotation of that part is indeterminate. And for ICA, we'll detect that rotation part, and finally can identify get the original sources. And for based on linear ICA, there has the assumption based on the sources are independent, and at the most one Gaussian of the sources, and this is a linear thing. And for this paper, the paper we're going to talk is about the nonlinear ICA, and by learning something of the nonlinear ICA myself, I know that because since it's nonlinear, we can have infinite possible ways to combine the sources and to get the mixture like the middle one. Still, we have the original sources, and the mixture will not only string or rotate it. And by using the traditional linear ICA method algorithms, we cannot get the original sources. And sometimes, but if you can get, and it's not identifiability, since the results are infinite, you can get the different kinds of results. And this is the problem of nonlinear ICA. And people do have many algorithms to resolve the nonlinear ICA problem. Like and they have some special cases on the data series nonlinear ICA, and they do kind of like the segmentation methods for their weights. And I will not go through about their logarithms, but the people who want to say, please stop me. And most of also, except for the specific kind of data, and most of the nonlinear ICA logarithms will condition on accelerate variables like the class labels, and like the shapes or some other variables can be conditioned using to predict the original sources. And but all of them are limitation because they are conditioned on something. And for this paper, they got kind of a new method with by using like the structural sparsity regularization and also permutation and mostly based on mixing part. For what the traditional ICA doing is we are trying to do like a unmixing direction, but this paper they're focused on the mixing part, and some preliminaries from the paper, which I think need to attach to there, and if one and which if there are later assumptions, their theories will call back a lot. Some of them are just basic mathematical definitions, but I still paste it there. So if anyone have a question of this.
Yeah, can you just go step by step? What are the assumptions?
Okay. For notations, there are for matrix, there's just represent the row and the column, the matrix. And for a set, if like the to do m by n and still the comments are is for the is represent the set of the column and the rows are same, and this represent number of elements in the set, and these three definitions should be very important, and like, but they give things, but I think the only matter is this sentence. It's just referred to the subspace of Rn and index of set S for like if S equals to n equals to 10 or S equals to 3 is like the for the I is not belongs to the 10, like it's just from 4 to 10 is that the I should be 0. The I represent the.
It's just the way it looks like they're just using it to zero out entries.
Yeah.
It's weird.
Columns, it's
Yeah, they have a lot of definitions, notations.
or no rows.
It's RN,
Yeah.
so it's a vector, but
And support of the matrix is basically the set of the coordinate of the matrix, which is non-zero.
No, but it's entire subspace, so the entries. Okay, but
What?
I'm thinking of data as columns. This is just a weird way to define all the common things that we already know: the row, the column, the subspace.
Yeah.
What is M? Is like non-zero matrix.
Or like a set is a set.
But why they call it a matrix? Matrix
Support of a matrix M. Like if we have
Support of a matrix. Okay, it's non-zero elements of the matrix, basically.
Subspaces.
Mhm.
Matrix and subspace is this thing, and the support of matrix is just basically indications that this is part of subspaces.
Yeah.
It's just
Yeah, I mean, there is nothing here, but it's the notation at first seems intimidating, but it's just like, okay, non-zero elements of matrix M. Fine. And then the second one is what? The rotated version? Oh no, what is M? Okay, it's a function.
Are we go here?
Yep.
And then they call into the sermon. I was trying to use my own words, but I'd prefer to copy their text there. And still going step by step. So F and F hat is a support of the Jacobian matrix of the FS.
did you list equations 1 and 2 in the previous slide? Did I miss? I don't think
I think I should, this is the 1 and 2.
Okay.
I should paste it there. And FS is a mixing function.
I see.
And the F has Jacobian for the estimated function. Estimated function. And here they denote another T, the logic matrix. Logic matrix is the elements with 0 and 1 corresponding to the support of which we kind of like when we talk about the F is the support of the Jacobian matrix, and the T is kind of is not a set. T is kind of a matrix to represent this kind of support. And they gave this for
So
assumption.
let's talk about what that is, because that's just going to be, like, you'd hope that that is close to the identity, right? And so it's looking at the diagonal of this matrix that is, so it's saying something about the scale of this space of this, of the Jacobian, or what is this matrix, right?
T.
No, this, well,
Oh, you
first
mean
start with
this-
so that should be the identity, right?
Hmm.
So T is the logical matrix corresponding to the support of that. It's just also just a vector of ones, or it's. I guess
But they do permutation with some part. I mean, missed.
F hat is a,
I've had is a evaluate estimated function.
I see.
So what is Jacobian of S? What, like, it's a
it's
Jacobian
a
matrix of function S, or what is S?
S is the source.
And F is.
F is the mixing function. Fs is the mixing function. And Jacobian is represent that.
And then you
Get
said
rid of
F hat is a permutation of the mixing.
No. I've had. I should.
Does it mean they define P just by junction,
Sorry.
customizability? Like, basically, if you're from sources to latent,
Mhm.
like to mixing, and you click out back. So it's like rejection. So take a point and you return another point and you can go back.
Well, yeah, but I assume F is, but then F hat is here, and so I was originally, I couldn't see the little hat on the F and the on this inverse by the multiplied against the regular Jacobian. So I was like, yeah, it's just the identity, but it's J of F hat, so this is a different function. So it's going to be something different, and I don't know what it is. What is F hat? It's just an invertible version of F, or what?
No, permutation, right?
Oh, it's an estimation of the mixing function. I see. Okay,
Ah,
that makes sense.
But you said up to permutation.
Well, it's a permutation in the abstract sense of permutation. Perturbation maybe is what he said. That makes sense then. So then this is looking, so T is looking at essentially the differences or the error in the estimation of F, kind of.
yeah. They
Yeah,
have
you can continue.
like they have like 2 pages of improvements.
Well, no, it's important to know what they're talking about,
Mm.
because it's not immediately clear what the purpose of all this stuff is.
Was hoping people can, and they get some for the assumption term. I just can keep pasting there.
No, but we need to understand what's written on that.
Yeah, I didn't
page.
see just that.
Yeah,
so
this is
I'm
too
still
quick.
Thinking my way through.
It's very compressed. So everyone agrees that the Jacobian is just the Jacobian matrix,
Oh, yeah.
even though it's written as a function of something. So it's is it a function, or it's a defined evaluated Jacobian matrix with values, or if it's a Jacobian matrix multiplied by a vector as like is it just a matrix, like a function with elements being derivatives with inputs outputs a square?
Yeah, it's just
For
that.
the ICA, so it's a square matrix. The traditional assumptions of
think so.
adversity. Okay.
I think it's just
A or the
Jacobian transformation of your sources.
Right, yeah.
It's like in other like papers, they talk about change your variable formula, and they have Jacobian, and they talk about probabilities. Here they just use kind of matrix notation or something.
Yeah, but It's not obviously clear to me when they write matrix as a function, what they mean there. Do they mean the result of that function, whatever? But basically, f and yeah, well, but there are two things. Well, the function and the evaluation point. It's not just the source; it's the point at which it's evaluated in the source. So S is one-dimensional vector. Or if it's
So all
like the
the
values
sources-
of all the sources at one time.
It's a matrix, or yeah.
I think it's also because if you have S and you have subscript like degree L, so they also like selecting rows. So I think the selecting rows like it.
Yeah, I understand when then it's a set of matrices. That it's kind of an abuse of notation. So if it's not the sources across time, then you have a Jacobian per time point. It's evaluated differently, right? The Jacobian at each point for function f, it will be different. This x inside or will change the s inside. But f and f hat are just non-zero derivatives, basically. Non-zero first order derivatives of those first function locations or something like that.
Right.
IJ locations of non-zero derivatives.
I don't think that matters so much. I mean, they could just be talking about this as like at one time point, and it should generalize, if you concatenate across time, I would think. That's how group
Maybe I
ICA works.
go to the
now.
paper.
But,
Don't really know how to close this on my screen.
what are you asking?
No. This
Functionally,
how to
just-
close this part.
We
and
can't see it on the screen.
I won't open the paper.
Oh,
Oh, maybe you're sharing just one window. You need to share the entire screen. Stop sharing.
I don't need. I can do that.
Yeah, stop sharing.
no, he's got.
I got it. I got it.
Hmm.
So I think you can jump to equation 77.
What?
And I think it will give you the definition for the Jacobian, or you can infer.
Oh, it's clearly a matrix at that current setting, at that current time point.
I don't think it's a problem. I think the notation there is the index of partial, the partial derivative of H with respect to S element Y. It is a matrix.
It's a function matrix.
Yeah, it's a matrix full of like it's Jacobian, the normal one.
Yeah.
But then when they say f, what they mean, because non-zero values of a function only defined at a point when you evaluate this function.
The capital F or the
Yeah, this calligraphic f.
So if function is constant, then your Jacobian signal will be 0. That's how many elements of that your Jacobian function is there.
But even for a non-constant function, derivative sometimes is 0.
That is only time dependent. But the
That
time-
is time dependent. That is input dependent. Forget about time. It is input dependent. Jacobian is input dependent. Is a function.
It is. Right. It's saying that what they try to do, right? They try to find the support vector, support element with F, the support element of the Jacobian function. And then they want to compare the differences. The one is the estimated one have a hat. One is the
Yeah, I see what's written there, but I'm trying to get the meaning because what is a non-zero element? Or let's talk about zeros. What is a zero of Jacobian? Only if the function is constant, then it is a constant zero function.
Yeah.
It is a zero function. That's your option. My option is evaluate the Jacobian, and sometimes it will be 0. And that's there will be zeros of the Jacobian too.
So like you add in the-
Because the things that
Yeah, you're evaluating, but you're saying, oh, okay, it's only looking at the constant
they're talking about, like the non
functions.
non-linear. If zeros mean the weight is not effective or influenced.
Yeah, that you're saying the same, what Jen is saying. If the function is constant,
this is
then
what the paper is trying to do.
But I don't know why you're even talking about the zeros of the Jacobian, because they're looking at the estimation, right? So the J of this estimated mixing function, f hat. So T is like you defined in the slides, you inverted, you put the inverse, on the other side of the equal sign, but T is essentially looking at the differences in the Jacobian of your estimated function and the true function that you don't know. And so that's what we're looking at the support at. We're looking at, in my mind, it's essentially like errors, right, in the estimation.
Yes, but at least they didn't say like Jacobian multiplied inverse of Jacobian. They used
Right.
the act like a support of Jacobian multiplied inverse of support of.
Yeah, it's weird. But
Also comes, they try to minimize some error estimation.
I think that's what that's what T is talking about, is some kind of error in the estimation, right? That can only be. what it's
are you in the right room?
Yes.
doing. But can we talk maybe then about this, what this theorem is saying beyond just what the Jacobian looks like? So
No, but even like I don't get what the Jacobian looks like. But okay, now we're just looking at constant functions. We only care about constant functions because only them will become functionally zero. But then this
Zero, right? Support is not zero.
Yeah, as a support is a set.
Of non-zero.
Yes.
yes, it's a set of non-zeros.
It is just.
No, set. It's a support. So yeah, set support of non-constant functions.
Yeah.
No, because we're not talking about non-zeros here. It's just
Right.
has no meaning. Constant, like zeros don't have a meaning when you're talking about functions. It's like, but then it's kind of like your, it's only up to permutation. We assume the scales are the same. Otherwise, Rogers, what you do to it to get the Marua-Mari index proper? Because when you multiply, if the scales are the same, like this ambiguity is removed, only then you can get an identity. Otherwise, you won't get identity because the scales are different, even though you can fix the permutation, maybe.
A inverse, the ground truth A inverse multiplies the. So it's trying to kind of.
Yeah,
that's what H is.
Sorry, I said A inverse times estimated A in the linear case. So ground truth A inverse multiplies.
They read it as F hat inverse there in H, right? F hat inverse.
Sparse matrix, sparse like permutation matrix, if it's in linear case.
All right.
It's the correct.
Okay.
I lost the F inverse time, Jacobian inverse times Jacobian. Where is it?
It's not in here. This is
Yeah.
something you would put in the slides, it looked like, or at least,
It's different definitions, right?
Ooh.
Different theorems.
I mean, it's implicitly there in the,
Yeah, I was looking for it. I can't find.
Oh.
Yeah, it sounds like a different theorem. You know the logic is for it.
Not.
they make an edit to this morning.
Just to mess with you.
Is it last modified 12th of January? So if you were.
Yeah, it's differently formulated. Yeah.
Oh.
But I mean, it's
Why?
there. It's like J of F hat of S hat is
No,
equal
the
to
data is here. For brevity, one.
No, where is inverse of Jacobian times? Okay, okay.
it's implicitly there. is what I'm
Yes,
saying.
yes, yes.
The thing I was
Right where you
copy and
mouse.
paste the search window.
Why did they do it?
I mean, I think we're getting too caught up in
Yeah, yeah, yeah.
notation.
They-
What are these assumptions? I don't entirely understand structural sparsity as an assumption. How do I interpret
And
what is it saying there?
First part is trying for and some
It's essentially a way of
so like
I think it helps if we think of the linear case. And they are putting a constraint on W and A that they are both sparse.
Right.
So that here they generalize to a nonlinear function.
Right.
And it's Jacobian being sparse. Then the only part that I guess I don't get are the assumptions 3 and 4.
So let's scroll back up.
But I mean, it's along the line.
Oh.
of sparsity. It's like the estimated support is more sparse than the ground truth.
No more sparse than the ground truth. No more dense than the ground truth.
Yeah.
No denser than the ground truth. No, it's not L0 norm. They defined it as number of elements. This is a set, and this is just number of non-zero elements. They redefined it in the. Yeah, if you look at the first slide of Yorong, there were definitions there in what you call L0 or well, okay, L0 is the count.
Yeah.
Yeah, yeah, yeah.
Cardinality.
Yeah, yeah, yeah.
But yeah, looks like they did have accompanying paragraphs for each assumption. So where was it, the paragraph for assumption 3? So it's, if you go down, maybe it's.
That's okay if it's not. And the one that I don't understand is 4.
Yeah, I don't understand.
and
for
for
you.
that part, they more like a methanes and
No, but
It's
it's not necessarily fruitful. It's just what they require for the theorem to hold.
Right.
Just
Yeah, I think we're digging way too deep into this particular theorem because all that they're saying here is that that this H exists, right? Or not that it exists, but that it has this particular structure.
it is based on this assumption is identifiable, and they give a mass improvement of all of the 4 assumptions.
I don't think we're gonna get much looking at the proof.
No, it's
yeah, let's
really
understand
is
what
a-
they're saying at least. Composition of
oh,
those
well,
functions.
this paper is different.
They didn't include the proof. in here.
Yeah. It's not the same. I'm sorry for inconvenient. What?
Isn't that in the subsection?
No, there is a bar there. I cannot click it. It's for
Yeah, there is implement if you want the proof, but let's understand the theorem first.
Is this their main result, this theorem? All right, I feel like I'm missing that there's something else maybe, and I'm afraid we're gonna get lost in time. Just looking at this first.
Yeah. We're just looking at the theorem, but we're not seeing what they're trying to show or what they managed to show.
there's proof.
What do you mean component wise? Okay, what if we assume that this is true? Some age, which is just a product or application, composition of two functions, inverse of the estimate times the ground truth. It's decomposable into invertible transformation. How is it useful for anything for the nonlinear ICA? Like where do they use this theorem? Do you get further?
I cannot get that.
Rogers, did you get further? Just like where are they using it? Because the results that they show on poster were very interesting. That Shenhui, you at the NeurIPS recap you showed. The results were interesting, applicable to like identifiability of ICA and even linear ICA. They added something to linear ICA understanding. So can you just go to the results section just to see? Okay, this is just a tool, right? This theorem, but how did they, why they used it or why they needed it?
And they have another theorem also. And this is the experiment result.
What is above experiments? What are they?
Yeah,
what are
they're
they claiming?
kind of
Okay, nonlinear ICA. Okay, let's go to this number 4. Yes. Nonlinear ICA with unconditional priors independent influence. So they have archive paper and they have open review papers and they're different. That's what is happening, right?
yeah, it's on the review.
You're looking at the open review.
Yes.
Okay. The new interesting result from the poster was that it's on identifiability of Gaussian sources, right? That was something like that because this corollary 1 from this theorem says that basically the source distribution is a factorial multivariate Gaussian, Rogers. That kind of relates to what we were talking about.
What page is that?
Page 4 of the archive version. It's right under that figure.
Which
Yeah,
one?
yeah. Look at this. The source distribution, the assumption 3. So they're looking at the source distribution as a factorial multivariate Gaussian. Factorizable, or what do it mean by factorial? Independent, spherical. Do you know, Rogers, what they mean by factorial multivariate Gaussian? The factorial part. Oh, so spherical Gaussian.
This is the objective function.
Oh, this is axis aligned, basically. Okay.
Well, what is factorial part exactly?
Imagine an ellipsoid that was rotated so that the major axis of ellipsoid are the basis of your linear basis. And then, it's not a sphere, but it's independent. It's just a product of marginals.
And how exactly is it different from the normal independent component? I mean, is it only different on on the access side? Like, is it like a 3D representation of it?
No,
I
in
didn't
the- in the-
understand it, to be honest.
In linear ICA, we can only have one Gaussian component for the ICA to be identifiable. And here they kind of quickly jumps to Gaussian. Everything is Gaussian now.
Oh, okay. Okay.
And yeah, exactly. And I'm lost there. Oh, why?
So
And no,
the idea that they're using a constraint, a sparsity constraint on the network parameters to enable identifiability, and as a consequence of that, they also get separation of source as a byproduct.
That's what I remember from the poster, but I don't see that from this corollary. Like they throw it in as an assumption, but basically they build toward separability.
From else,
Mm-hmm.
and then the conclusion is that they are recoverable.
But I
Isn't that what they call it?
uh, so how do you interpret these words? Yeah, component-wise linear transformation, and again, what they mean by component.
Well, I think what this is saying is that you still have residual linear descent. This corollary, I think, is just handling the nonlinearity. And then with section 3.2 on proposition 1, maybe is where they handle they add the structural sparsity and handle the full separation. Does it make sense?
Mhm. So proposition 1 in section 3.2 is about linear ICA now.
With Gaussian source. And the assumptions are pretty much the same as theorem 1, but now for the linear case. And the conclusion is that the learned A matrix is a scaled permutation of the true A matrix. And that's the condition for identifiability.
And since they're not talking about spherical Gaussian, we will recover, I mean, that's easy, kind of PCA will recover the ellipsoid. So what else do they add? Because it will be an ellipsoid in both cases, in the PCA case and the ICA case of this sort, the same ellipsoid. It's only like recovering that sparsity. Additionally, that PCA doesn't make this extra step to.
There is no requirement that the variances be different from each other.
So they could have a sphere, like a ball, and there is a preferential, because of sparsity, there is a preferential orientation, because you need to create a Gaussian by a product of sparse things,
Yeah, that's.
and that gives you additional edge.
You was constructed using sparsity. So if your generation process is sparse in nature, that does something to the end mixture that sort of leaves traces in there of how to recover it. If you have the sparsity built.
Yeah, we need to figure that out. That's like I assume that's true, but that is a pretty cool result. Everyone see what at least Rogers had said? Like we have this central limit theorem, mixture of multiple sources always leads to a Gaussian. But this one says, oh, wait, our original mixture of sources already separated, not a mixture, but a product of sources is a Gaussian. So the mixture transformation will be Gaussian no matter what, central limit theorem. But this says, oh, we'll start with a Gaussian, right? But the Gaussian is it's kind of weird that the marginal distribution of that Gaussian are formed by specific sparse constraint or something like that. This one I don't fully get. But if there is this additional sparsity constraint on the sources, or
The sparsity is- it's on the mixture matrix, the A matrix, not the source. Sources that discuss.
the sources are Gaussian from the start.
If the G matrix is sparse, or
The mixture is Gaussian.
you're mixing a field source
At a time.
at a time. So you're putting a constraint, like your microphone only has signal from 3 out of 10 people in this room. And no one else's voices are in that one microphone.
Mhm.
The next microphone has another set of people. And no microphone has all people in there. So all microphones are sparse mixtures of the sounds in the room.
Oh, that's what they call the microphone is a component that they like what they call a component, right?
Microphone.
They continue to use a word component, composition of component-wise linear transformation and permutation. Like here and there, they use this component thing.
But if you have like different types of microphones, so basically you have multi-view, like you can generate as many multi-view and samples.
Here, of course, I'm just describing the assumption that in this setting, there's no dense mixture. No microphone detects all voice.
Yeah, this is a
Yeah,
what
understand, but
what
so they need to find the structural sparsity somehow. Do they just sample another design or what do they do?
No, it's an assumption, right?
Yeah.
They can simulate it. Let's simulate data with that properties and demonstrate that it decomposes back, like that you can recover the original sources.
But then this is not different from multi-view approach,
Probably, but what?
because there is ICA paper with multi-view approach also for the identifiability with multi-view approach.
Well, then we need to dig into this. Do they cite that paper? I don't know. What is it called?
to mention the things here, but to decide the paper.
Yeah, you imply sparsity, you basically, like, for example, there are some models that there's an object like dog running on like background, and some models can distinguish dog from the background. It's already like I see it, right? But it's far from the data structure. So basically, they're trying to say that there should be, like, just assume if, like, I don't understand, maybe theoretical won't be the case for me. Just for example, you're training a neural network, you have activations, and some activation will be activated more for some specific signal, and for some other signal, it won't be activated. So basically, like cutting the same. You have some dimensions that will be activated for some case, and for some case it won't be. So it's in some sense sparsity.
Yeah, this is what the paper do. Right. But what
Source.
Or I'm just saying that in the sense that, like, how it will be like in real life, like if we activating on specific things, or like we have like multiple microphones So it's basically multi-view in some sense. There will be like intersection between features that like microphone will capture, and then with this will allow to separate them. Which
I think I understand what you, but, oh, I'm. Maybe the problem is that I don't understand much of the multi-view definition. With this
like
particular,
example, you can take you can make a photo of a dog from two views. And this will allow you to separate the dog from the background.
are you assuming that the background doesn't change?
No, you just take a photo of laptop, for example. I'm taking from the asset side and from William's side of my laptop. And you already can separate, right?
You're not really describing the separation process, Alex.
Yeah, I don't. I'm saying that example there is like another paper from Luigi.
Background and dog are independent. But they both are present in both views.
I understand, but like you can mask out something, for example, or like turn off the microphone at the same, like you generate two different views of the same entity in some sense.
I guess the difference that I understand of the assumption for this paper, though, is that you'd have like 5 cameras and one of them doesn't see the dog at all. And some sources are not detectable in certain.
Yes, there is, as I already said, like I think they have example in the workshop papers that you in a like zoo and then different animals, and they assume that zoo is not full of people, so even like these animals will move around. They have like locations, or like they will have sound. Then this will allow rate separate this stuff.
I think combining what you said with what Brett said, that makes sense, that no image is gonna have all animals present. Right? Because everybody's spatially separated.
Yeah.
But
every animal.
Yeah, but there is another condition that we're not hearing. Imagine you have 4 sources and 2 microphones. One microphone only measures source A and B, and another one measures source C and D. Yeah. Those are 2 separate non-identifiable ICAs. So you have to have cross views like required. I don't see there's theorems maybe too, like they have. But if they not, like it splits into the same smaller size, but same problem as we had before.
Here in those parts, specific views.
I'm talking about the conditions that they're putting here. I didn't see that condition.
Yeah, so proposition 1, this structural sparsity.
Yeah, but structural sparsity doesn't require conducted graph, or does it? Like the graph should be con.
See, it's an intersection. So if your intersection is empty, it's violating the assumption.
So, okay, so they're saying only for the non-empty intersection it will work. Right, so that's basically they're trying to say what I'm saying,
I
that
think so, yeah.
it has to be in at least 2 views, or at least picked up by at least 2 microphones, one of the sources. So,
Basically, it's a Jacobian that we had the safe like logic matrix. In some sense, probably this logic allows to identify kind of different sources. It basically contains like configuration, like assume it's like binary, something triggers things. You have like this sparse function.
no, the Jacobian tells you which things change together. And
Yeah, but this
so-
way, because of it, you can identify. Because for each kind of thing, you will have different kind of logic models.
Logic matrix, that confuses me, but yeah,
Because when we converge, for example, for the model, we want our model like be sparse and like activate to specific things. And this way we can separate, right? Because otherwise, if we have like cat and dog and we have same activation logic methods, we won't identify anything.
yeah,
Same. But there are other theories for things like rotation that I think are necessary.
Gotta head over to DMAP.
Yeah.
Use that analogy.
You still have 1 minute, come on.
Generate signal. Then that model will work the way you described. So if you sort of think kind of like an encoder.
But I think that the assumption is that
They did the same.
it's already sparse in the beginning.
We have another talk next door, right, starting right now on brain anatomy, and you probably want to hear that talk. If you know, if your brain anatomy is not as good, then that could be useful. But thanks, Yorong.
Thank you, everyone.
We need to continue digging into
Yeah.
that.
I would